Hello, welcome to the Module 5 Topic 1 review. If you're in my class, then chances are you have a test on this very soon, maybe the next day. Or maybe you're going back and watching this for the test corrections, which is great. What a great option for you to take. That's amazing. Glad you're here. Yeah. Here's what you're going to need. You're going to need your review sheet. I have one on this notebook document that I'll be going through. But most importantly, you'll need a TI-84 calculator, which if you're like me on a computer is like this, okay? So here's mine. I have one in physical as well, but this one works on the computer and it is called Wabbit Emu. Your school computer will have in the company portal. So you just type company portal into your search bar like down here, and then you type in Wabbit Emu. Wabbit, it's rabbit with a W. And from that point, you just download it and you have a TI-84 on your computer. And it works exactly the same, right? So you can turn it on. Okay, maybe it doesn't work. It works. Spoilers for the first problem. You can also reset it like you normally would. Second plus 7, 1, 2. So if you're watching along, go ahead and reset your calculator. Always a good idea before you start doing anything, because who knows what was working on that calculator before. Might be wrong answers, okay? This is going to be just one full video. The last time I did this, I sectioned it into questions, and that was really annoying. Instead, I'm just going to upload this full thing. Hopefully it won't take too long, but you can check the description. So if you're watching on YouTube, your play bar will have little timestamps on the bottom, and you can just go to what problem you need. If you check the description of the video that's in Teams in the stream tab, hopefully they'll be there as well. So otherwise, you might just have to scrub through the video and find the problem you want. But if you're just sitting, relaxing, hanging out with me, watch this full thing, well, good to see you. Let's get started. What do you think? Okay. Problem number 1. So this is the same exact review sheet that you have. I'm going to explain my thought process on all of these problems, how to do them to the best of my ability and what I'm looking for. Once again, you do not get notes on this test. However, you will have an opportunity to correct, and if you can do this, you should feel pretty confident on the actual assessment, okay? We have our calculator, we have our brains, and we have our writing utensil. And really, what more do you need in life, okay? So start off with number 1. Analyze the function f of x equals 2x squared plus 4x plus 4. Whoa. Sketch a graph of the function using your calculator. Okay, that I can do. Determine the absolute minimum or maximum. Well, what that tells me is to just graph it in my calculator. So here we are. Once again, to graph anything in this bad boy, you're going to go to y equals. This is super important. Each one of these lines is a different function, so you can enter as many things as you want. Well, 9, I guess. But you just type it in. So I just type it in exactly as is, 2. X will always be this button, this x, comma t, comma theta, comma n. It's just any independent variable, so hit that. Square, you can square it right here. You can also do the caret too, but that's annoying because you have to scroll out. So just that squared plus 4x plus 4. Once you have something graphed, just hit graph, this top right skinny button, and let's see what happens. We're working nice. That's pretty good. If you're sure you entered the same thing, but it doesn't look the same as mine, your window might be different. To get back to this normal window, this -10 to +10 in both directions, hit zoom 6. Zoom and then Z standard is what it said. And that brings you back to your standard window. And that's always what happens when you reset your calculator too. So there we are. Note that this does not match our graph here. So we're going to look a little different, right? Our axes. You could make these axes your window as well, but I'm too lazy to do that. And we can do it from here. Okay. So here's what we need to figure out. We need to figure out the maximum or the minimum. Well, first things first, every parabola will only have one or the other. It will only ever have an absolute maximum or an absolute minimum. And in this case, because our parabola opens up like a cup, we will have a minimum value. Now, I could probably look at this with my eyeballs and see that it's like there, whatever that is. But here's the tactic to find it no matter what, okay? It's second trace, which if you've been practicing and following along with calculator throughout our lessons, you've used this so much, okay? Second trace, and because we want to find the minimum, we go to minimum, okay? From here, it's going to ask the same 3 questions every single time. Left bound question mark, right bound question mark, and then guess question mark. Okay. Your process is also the same every time. For min or max, you go first to the left side of the function, anywhere to the left, so more negative than your vertex, right? Your max or your min. So right here works for me. Boom, hit enter. And then you say right bound, scroll anywhere to the right side. Make sure that it's definitely on the right though. Hit enter. And then guess question mark, just hit enter again. Don't type anything else, just hit enter. And you should get this, -1, 2. And that is my minimum, which is right here. Okay. If you did the exact same thing I did, but your calculator says -0.999999 or -1.000002, whatever it says, if it's super close to -1, then it's just -1, right? This is just -1 here. Okay, so that's good. That's half of our question. Now we just need to sketch it. We just need to sketch our parabola based on this graph, okay? So in order to sketch a parabola, I like to just have a couple of points on either side. That way I can generally find the shape of it. I know what a parabola looks like. It's a U shape or an upside down U shape. So if I just know a few exact points, I'll be good. One of those is the vertex. So to sketch a parabola, you will always need the vertex. And then, I don't know, what's a nice point somewhere on the right? It looks like I can find the y-intercept, which happens at 1, 2, 3, 4. So right there is a point. Because my parabola is symmetrical, since this is a distance of 2 away, on this side, I will also be at that same height, right? I'll be -2 away from my axis of symmetry, my middle. And so I think this will be enough for me, and I'll just sort of sketch it something like that. That's not too bad. That's actually pretty good. I'm pretty proud of that one. Let's compare it. It is going to be a little bit different because our windows are different, right? We're looking only between -5 and 5 versus -10 and 10. But I'm pretty happy with this outcome. So I would qualify that as a sketch, and I would qualify this problem as done. Oh, I forgot to put my name on the paper. Don't do that. Okay. Or don't forget that. I don't need the check mark. Okay, moving on to question 2. So here we go. This one says, complete each table to calculate the first and second differences. Ooh. Label each question as linear or quadratic. Okay, so I've seen some people answer this problem already, and they're a little confused on what to do. First, second differences. I guarantee this one small symbol will change your idea of this problem, and it's this. That's supposed to be an arrow. That didn't look great. Like that, right? And now, I think immediately that signals to you, oh, how do I go from -3 to 1? Well, I would add 4. How do I go from 1 to 5? Well, I would add 4, right? That's what this is asking. Find the differences between these numbers in the table, just the y values, okay? 5 to 9 is also +4, and 9 to 13 is also +4. Then the second difference is the same exact thing. You say, what's the difference between 4 and 4? Well, it's 0. What's the difference between 4 and 4? 0. What's the difference between 4 and 4? It's 0. Okay. And that completes the table, right? So that's good for that one. But now we have to figure out what this means. What does this tell us? Well, first differences you can think of as rate of change or slope, right? And if your first difference is always the same, that means that you have a constant rate of change. And if I know anything about functions, there is only one type of function that has a constant rate of change, and that is a line. And lines are liner, linear. Oh, so this must be linear. Yes. So if your first differences is constant, meaning your constant rate of change, it has to be linear. It's definitely not quadratic, at least. Okay. Let's see about this next one. So I'm going to do the same exact process. How do I get from -1 to -3? Well, that's actually down, right? -3 is less than -1. So I would subtract 2. And then to go from -3 to -1, that's back up. So that'd be +2. And then 1 to 5 would be, well, negative 1 to 5, sorry, would be plus 6, right? I have to account for the negative 1 and then 5 more. So that's 6. And then 5 to 15 is plus 10. Okay. So right away, this statement, constant rate of change, does not apply because you see that these numbers are all different. However, when we dig one level deeper, inception, if I draw this arrow, how do we get from negative 2 to positive 2? Well, I would add 4. 2 to 6? Oh, I would add 4. 6 to 10? You know I'm adding 4. And what this tells us is that our rate of change is not constant. We are changing our rate of change. That's what this thing is. Okay. But if our second difference, in other words, our change that we're applying to the change, if that is constant, then it is quadratic. And that's just a fact of life. We saw that from the handshake problem, actually. If you remember that from like one of the first days of class on this unit, we did a problem where we would model how many handshakes a group of people would take. And people saw that the second differences was constant. You would add 1 to the second difference every time. So that was pretty cool, and it had to be a quadratic function. So there's our answer, quadratic. Okay. And that's it for this problem. Okay. I like my use of red and black as well. Very nice. Okay, moving on. Number 3. Another linear / quadratic. This time, instead of from a table, we're using our eyeballs with a graph. Okay. So we have to label each graph as linear or quadratic. We have to identify the x-intercepts. Okay. So this one is easier, and so I'm going to start with it. This is a line, believe it or not. If I were to ask you to describe this shape, you would probably say a line, and that should hint to you that it's linear. So that would be your answer here. And then an x-intercept is just like a y-intercept, but on the x-axis. Where do you cross? Well, you cross at this point right here. Let me make it a different color. This point right here, which is the point -2, comma 0. That's your point. X is -2, y is 0. I'm not happy with that 2. I'm going to rewrite it. I'm using a tablet that I haven't used in a while. Okay, so I'm still getting my sea legs here. Okay. Anyway, that's my x-intercept. There's no other one, so no x-intercepts, just x-intercept. Okay. However, when I look at this thing, this is a parabola. I can tell because it is the way it is. No, I can tell because it certainly is symmetrical. It has a vertex, and the way that I'm growing indicates that it is having a constant second difference. Whatever that means to you, you can tell. You can define a quadratic or a parabola by looking at it. And for the sake of this class, if you see this shape, it's a parabola. Okay, it's not a catenary. I wouldn't throw that at you or something like that. Crazy. Anyway, so this is a quadratic. I literally can't draw. Here we go. Quadratic. But now we have to find the x-intercepts. So here's what that means. Same thing. We're going to look at where we cross the x-axis. And that looks to be right here and right here, which is kind of nasty because it's not at a nice point like this one was. So we kind of have to use our judgment and figure out what fraction or what portion of the line did we really cross at. So it's not at 2, but I would probably say here's a half, right? Here's 2.5. That looks to be about half of a half, which is a quarter or 0.25. So I would say that this is at 2.25 in the x direction, which means it's at this point. And then this one is the same thing, but 2.25 lower than 0. That's negative 0.75, comma 0. And so that's where this point is. And so my x-intercepts would just be that. It'd be negative 0.75, comma 0, and 2.25, comma 0. Those are my two x-intercepts. Okay. It's important. The x-intercept is a point, right? It's a coordinate point. If I say the root or the 0, then it's just the x value of those. But the x-intercept is technically the coordinate point. Okay. So boom, there we go. That's all I have to do. Look at the way it is, what it looks like, and then find where it crosses the x-axis. All right, I'm ready to go to the next page. We finished the first one. Done. Here we go. Back to the calculator. We didn't need it for a while, but now we will. Number 4. Okay. This is a projectile motion problem. Think Punkin' Chunkin'. That's the one we did it as an example in class. But in this case, someone's going to kick a ball. So if you think about like a goal kick in soccer or maybe a field goal in football. I said football both ways anyway. Sip of my water. So we're kicking this ball off of the ground, it looks like, and we're modeling how it flies through the air using this function. Okay. I will always give you the function and the type of function that you will need to use for a quadratic projectile motion problem. Okay. And this element right here, this negative 16t squared, this has to do with gravity. And then this 40t has to do with that initial vertical velocity. Okay. So we're kicking it pretty hard. And we're not on the moon. So we do have this amount of gravity. Okay. But there's a hint here, and it says calc, which means we need our calc. Okay. And so we're done with this function. So I'm going to go back into y equals, clear this, and now we're just going to enter this g of t as y1. Keep in mind, so even though it says t squared, we just use x. We still use this one. So we're going to type in, and this is also super important, because this negative 16 is in front, it's not being subtracted, you got to use the negative sign, which is this one down here. Okay. If you type it in and you get syntax error, then you used this one, which is a no-go. So instead, if your number is alone or in front, use the negative button. Okay. 16x or t squared. I know I just said in the last problem to not use the caret. It's complicated, but I did it. And then plus 40x or t. Okay. And then let's hit graph and see what happens. If we're lucky, we won't have to change the window. Okay, well, never mind. We have to change the window. It looks okay. Like, we're definitely looking at a decent portion of it, but I'm missing the most important part, which is the peak, the vertex, right? And I'm not seeing the full picture. So when you get to here, this is a good indication that we got to change our window. So let's go into window. Okay. And here's what we have to change: our x-min, our x-max, our y-min, and our y-max. So x-min and x-max is left to right. So x-min is how far left you need to look. X-max is how far right, right? So for these projectile motion problems, and if you're thinking about like any sort of experiment, what's the time frame that you care about, right? Remember, x is measuring time, or t, right? So the first time that I really care about is when the ball is kicked, which is at t equals 0. That's when I start, right? Start measuring the time in the air. And then how long do I think it's going to fly? I don't really know. But if I go back to my graph, I can actually see where it comes down. It comes down actually about 3 seconds. So I don't need to look that far. Just for the sake of making it look nice and neat, let's say my max is 5. Doesn't really matter, but I'll choose 5. And then your scale is just how far apart the tick marks are. I don't really need to get specific, so 1's great. Same thing for y-min, y-max, except I'm thinking up and down, right? So how far, or what's the lowest point I care about? Well, it's the ground, which is at y equals 0. Okay, so I'll make my min that. And then how high do you think I will kick in the air? Let's say, I don't know, 40 feet. That's pretty high, but actually that might be too high. Let's try 20 feet. Okay. And let's hit graph. Oh, well, that's better. That's better for sure. We're looking at a better picture, but I still didn't look high enough, right? So I need to change my y-max. Okay. Maybe my initial guess of 40 was a little bit better. So let's go back to that and then hit graph. And that's much better. Yeah, that's a full picture. Okay. So here we go. We have to answer 3 questions using this graph. Okay. But they can all be solved in the second trace, which is calc. Okay. Super important in this menu. This first one asks us, what's the height of the ball after 0.5 seconds? Well, you could solve this algebraically by plugging in 0.5 for t and just solving it or evaluating it. But I'm going to show you a little trick. If we have it graphed, like right here, we can go second trace into value and then type in any value of x you want. So because I want 0.5 seconds, I just hit 0.5. And guess what? It tells me how high the ball is flying. Y equals 16. So I know that after 0.5 seconds, my ball is at 16 feet in the air. Okay. Or y equals 16 feet. Also be a great answer. I just said it right out. Just feeling crazy. Okay. And then you might want to think, okay, 18 feet. Let's go second trace value 18. But guess what? That is not an x value. Height in this case is y. So this is looking for the y equals 18. At what time? Ooh, okay. This one's a little more tricky. So I'm going to give you a couple of options. Number one is the best way to do it, and number two is a little shortcut. Okay, so here's the best way. I basically need to figure out where my graph, what part of my graph is at 18 feet in the air. Okay, so what I'm going to do is go back into y equals, scroll down a line, and type in just straight across horizontal line at 18. I want y equals 18 to be on my graph. And check this out. Now I get that straight across line right at these points, and I can find exactly where they intersect, exactly where they cross. If I go to second trace intersect, which is 5, it now gives us a couple of options. So now it's going to ask us 3 questions instead. First curve, second curve, and guess. Okay. So first curve, just like your parabola. Note that I'm picking somewhere off to the right here. I hit enter. And then second curve, I just hit enter again. And then guess. And it tells me I'm at 1.91. So my first answer here is x equals 1.91. Now, however, this is not the only place that I will be 18 feet in the air, right? I'm going to kick the ball up, and then it's going to eventually come back down. So I also got to find this point on the left. And I do that by also going second trace intersect. Except for this time when I select my curves, I just need my cursor to be a little bit closer to the left side. Oops. I just need it to be nearer to this left intersection. So I'll just hit left until I'm there, and then there, and it should give me, boom, 0.58. So x equals 0.58. And these are my 2 answers, okay? Seconds. Why did I do it in a different color? I don't know. X equals 1.91 seconds and 0.58 seconds. And there we go. Okay. So that's kind of tricky. The other option, of course, would just be to scroll around and see if you can find it. But it's not going to be exact. Like, so you can look. That's the closest I can get, but it's not perfect. And then if I scroll over, same thing, right? Not going to be perfect. But that also works. Okay. I don't need that line anymore, so let's get rid of it. Because now I didn't answer part C, which is saying find the maximum height the ball reaches, just like the old days. Second trace into maximum. And then left bound, we have to select somewhere on the left side of our curve. So I'm going to scroll all the way over until I get to the left. That's on the left for sure. And then scroll to the right. That's on the right for sure. And then hit enter. And yeah, I get y equals 25. And then my x is 1.249999. As soon as you see these 9s, you know to just round it up a little bit. So this is 1.25. I realize it's kind of hard to see on the screen, but it is 1.25. So the point is at 1.25 seconds, at 1.25 seconds, I reach 25 feet. And that came from y being my up and down, my height, and x being my time, which is in seconds. So I get these 2 answers. 1.25 seconds, I reach height of 25. And that's it. That's a tricky problem. A lot to do in the calculator, but the calculator can solve it all for you. You just got to know what to do. Okay. Boom. All right. Super fun one. Keep in mind, if you have my copy of the review, I'm sorry, this should be plus. Should be +5. I didn't notice it because, well, I used the graph to solve it. And so I'm going to just use the graph. But that is this function, minus 4x plus 5. Minus the 5, that helps. Okay. So we have to answer all of these questions just using this picture. And it's doable. We can do it. Okay. We just have to know what they're asking, what they mean. So let's figure that out. Number 1, domain. This is on my board, by the way. So if you're in class right now watching, look up on my board. It's on there. Domain is all possible x values. So I'm talking left to right. Where does our graph exist? If I move left to right, where does my graph exist? Well, keep in mind, it's a parabola. It goes on forever. So in this situation, yeah, it would go on forever like this, infinitely. I know I didn't write the arrows, but that's okay. And so if I think about going more and more left, my graph is still heading in that direction, right? I will always have this parabola exist to the left. So no matter where I go, all the way to negative infinity, this parabola will still exist. And then if I go to the other end of the universe, positive infinity, guess what? This parabola is still heading towards that. It would still be there. So thinking about left and right, there is no place I can't go, right? I can hit every single thing. What that means is our domain is all real numbers. Okay, that's this symbol. If you want a shorthand, it's called blackboard bold R. Okay, that's how you use it. Here's a hint: if you have a parabola, just in like coordinate space, just graphed out, the domain is always all real numbers. Okay, assuming it continues on forever. Okay. The range is like the domain, but it is all possible y values. So thinking up and down. Okay. So this time, I'm thinking if I start at the very bottom of the universe, all the way down here, does my graph exist? Yes, it does, right? It's over here somewhere, right? It's continuing down. But as I go up, I eventually reach a maximum point right here. If I look above this point, there is no graph. There is no line. There's no parabola, right? Sure, there's graph and line and coordinates or whatever, but this parabola does not exist up here. So this area is not in the range, which means that I need to verbalize that I can go all the way up to 9, right? That's what I need to say. Y, every y value is up to 9. And I would say that by saying that y, everything y is less than or equal to my maximum point, which is 9. Right? I can get there. I can touch it, right? I'm at 9, so I would say less than or equal to, and this would be my range. You could also say this like this: negative infinity to 9. That also works, right? But that makes sense. Y is less than or equal to 9. That's what they do to Matthew as well. Okay. Now we're back to some stuff that we've done a lot. I mean, we did domain and range a lot, but y-intercept, x-intercepts. Y-intercept, I'm looking for the point where I cross the y-axis. It happens right here, which is at 0, 5. Right? Remember x, y, so I don't move in the x. I'm at 0, and then my y-intercept's at 5. X-intercept, same thing, but on the x-axis. So we're looking right here and right here, which happens to be at negative 1, 0, and 5, 0. Nice. Those are my x-intercepts, right? Just right here and right here. Keep in mind, those are coordinate points. Different from zeros, right? Different from zero slightly. Okay. You should feel comfortable with that. I really want you to put it in coordinate points just so you understand that an intercept is a point, a 0 or root is a value. Slightly different. I know it's kind of, I don't know, annoying, but that's how it is. And also just understanding that as an x-intercept, your y value will always be 0, or as a y-intercept, your x value will always be 0. That's helpful to know when you're thinking about conceptually just thinking about a graph or a table or something like that. Okay. All right, moving on. Axis of symmetry. We have a formula for this. We're actually going to cover that later down the road, so be excited because we're going to do some calculations of axis of symmetry. But if you have a graph, if I asked you, fold this graph in half, right? Fold this graph down the middle. Well, what would you lean to? I don't know. I think you'd probably not fold it like this, hot dog way, or whatever you would say, or hamburger. You would instead fold it down the middle like this, right? That's just what catches our eyes. Parabolas are symmetrical in nature, and they happen about the middle, right? It's symmetrical about this line, which happens at x equals 2. So, in fact, check this out. Do a little dashed line to signify that I am at my axis of symmetry. That was so bad. I tried to draw a straight line. It didn't work. If only there was a tool to draw a straight line. Oh, guess what there is. There we go. There's my axis of symmetry. It's at x equals 2, right? That's just the x value that it's at. The axis of symmetry and the vertex are related. They always happen at the same x value. The difference between the vertex is that it is a point, right? It's the actual coordinate point that exists on the graph, which in this case is all the way up here, 2, 9, right? That's the y value, just x, y. All right. Last two questions. Interval of increase, interval of decrease. Well, how would I answer these? This is almost like domain and range, I would think about. It's almost like domain. But I'm thinking about how I'm moving like through my graph, right? If I'm moving left to right, what am I doing? Going up or down, and where, right? So the interval of increase in this case is going to happen anytime you're going up the hill, right? Imagine you're on a roller coaster. You would start all the way at one end of the universe heading up, chugga, 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 right? You would go all the way up until you reach the tippy top, in which case you stop for a second. Your anxiety is at the highest point. You're about to scream because you're going down the hill, which means that you have increased from negative infinity to 2, right, in the x direction, all the way over here until I get to x equals 2. I'm increasing. But then, as soon as I hit the hill, as soon as I hit the peak, I'm heading down, right? I am now decreasing. I'm heading down this roller coaster, which means decreasing, my interval is 2 to positive infinity. And I'm heading down this roller coaster for all of eternity, which does not sound very fun. Leave a comment if you would ride on a roller coaster on the downward part of the hill for the rest of your life. I wouldn't. Okay. Anyway, that's problem 5. A lot of stuff there. Every key feature of this graph, but guess what? You can nail it just by looking at the picture. You just gotta know what it means. Okay. Just gotta know what it means. All right, number 6. 6, 7, and 8, all about writing functions. So I'm gonna go a little bit of a tangent, a little bit on a side note. I'm gonna talk about these again, but here are the 3 forms of functions that we have for quadratics. Okay, number 1 is general form. General form looks like this. It is a x squared plus bx plus c, okay? Where a is the leading coefficient. You'll see that a lot. In fact, it's in every single form. Co-F stands for coefficient. I'll write it out. This shit. B is some weird value. I don't know what it does. But then C is the y value of the intercept. Of y-intercept, right? That's where you go up. Or you can also think of it as a vertical shift, up and down. Okay. Either way. Let's say shift. So that's what you can tell. If you know these things, if you know how far you go up and you know the leading coefficient, use general form. Generally we use general form for just graphing, like plugging in. It's the nicest to type. So like this, that's what you use it for. The other types are this. We also have factored form. And this is helpful when you have the x-intercepts. If you know the x-intercepts, then you can write factored form. It goes like this. You have the leading coefficient again, a, times x minus r1 times x minus r2, where you guessed it, these r1 and r2 are the zeros. That's the x value of the x-intercept. It's where you cross in the x on the x-axis, okay? And then a is the same thing. It's the leading coefficient. Remember, a, that leading coefficient determines how wide or how narrow our graph opens, okay? And also whether it opens upward or downward. And then last but not least, we have vertex form, which is helpful if you know the vertex. But here's how it looks. A times x minus h. All of that is squared. And then plus k. Okay. K and C are super similar. In fact, they're pretty much the same. And H is kind of like B, but a little bit different. So I'm not going to talk about it that much. But this, sorry, I'm going to rewrite that K. That looks awful. Plus K. Does that look like a K? Looks like a K, I guess. Anyway. These 2 points are important because the value, or the coordinate point, H, comma, K, is the vertex. Right? So if you know the vertex, you can write vertex form, as long as you know which way it opens, something like that. Okay. I want you to note real quick, sorry, this is a long aside, but I want you to note that in the factored form and in the vertex, you always subtract inside the parentheses. That's because you're changing the input, okay? So if you think back to like transformations, you do the opposite. It's inside the function. That's because of the subtraction, right? We're changing our input x, so it has to account for that, right? It's what value of x makes it 0. Anyway, so the zeros are just the number without the minus sign. So if you subtract 2, then your 0 would be 2. If you add 6, then your 0 would be negative 6, something like that, right? And then h, same thing. Same thing for h. Okay, so I'm going to copy this on the next page as well because I think we'll need it. But this is enough to answer our questions here. So let me just move this down real quick. Hello? Here we go. There we go. And let's answer these. So I know, like they gave it to us, factored form. It says, use the given information to write a quadratic function in factored form. The parabola opens downward, and the x-intercepts are 6, 0, and negative 2, 0. Okay. Well, if I have the intercepts, then I can write in factored form. And here's how. All I have to do is take my factored form equation, which is this. There's an a. We'll talk about that later. Minus r1. And then another set of parentheses, x minus r2. And now it's my goal to figure out what's a, what's r1, and what's r2. Well, it's just r1 and r2 are just the x values here, right? So I can just substitute those, replace those. So 6 is my first 0. So I know that in my first set, it should be x minus 6. That's from right here. And then, because this one's negative 2, I'm going to actually subtract negative 2, right? But subtract a negative minus a negative is a positive, right? It's plus. So we're actually, you could write add 2. But just note that this 0 is at negative 2 because we added. Do the opposite. Think of it like that, maybe? I don't know. Anyway, so that's almost done. We incorporated our zeros, but there's one more piece of information. It's this a, okay? And the way that we decide what a is actually in our equation. If we look, the parabola opens downward. Down like a frown. Oh. And if I'm frowning, well, I'm certainly not positive because I'm frowning. I must be negative. So all you have to do for a is pick any negative number, whatever one you want. You can make it negative 1. You can make it negative, I don't know, 2. Or you could just make it a minus sign. That's also negative 1. But there you go. Boom. So that's it. So that is your factor form equation. You know what? Let's give it a name. F of x. You know, give your functions a name. You wouldn't buy like a pet fish and then not name it. You know, so give your functions a name. Doesn't matter what you call it. You can call it whatever you want as long as it's something, some function name. I could have called it p of x. I could have called it I don't know, z of x. That'd be kind of confusing, but whatever. Doesn't matter. It's f of x. That's what I call it. All right. Give your functions a name. On to 7. I'll do all these problems in one go, so it'll be the timestamp 6, 7, 8, because they're all kind of the same. Determine the axis of symmetry for the parabola where the x-intercepts are negative 4, 0, and 10, 0. All right, well, we talked about this a little bit in this problem. The axis of symmetry happens in the middle. Well, one way to find the middle of a parabola is to take the midpoint or the average of your two zeros, right? And so you just need to find what's in between your two zeros. And the way to do that is to, well, there's a formula for it. It's like this: R1 plus R2, and then divide by 2. That's also just taking the average of the two values, right? Finding the middle. That's how we do it, right? If you want to average your test scores, add them all up, divide by the number you had. That's how you find the mean, right? So in this case, our R1 is -4, and our R2 is 10. So we go -4 plus 10, and then divide by 2. That is -4 plus 10 is 6 over 2, which is 3. So the axis of symmetry is at x equals 3. And that's your answer. Right? I just found the middle between the two zeros. If I did the same thing here, right, I'd say -1 plus 5, that's 4. Divide by 2 is 2. And guess what? Our axis is at x equals 2. All right. Number 8. Here we go. So there's two ways to do this one. You can do it algebraically, or you can do it graphically. I am fine with either. And honestly, I would do the graph if I were you, but let's do the algebra. Okay. So to do it algebraically, and by the way, if you want to see it graphically, and let's do the graphically first. Let's do the graphically first, because I think that's the way most people are going to do it. That way you can just skip the rest of this problem when you're done with it and move on to the next timestamp. Okay. So let's do it graphically. What I mean by that is, well, use our calculator to graph it, right? We have access to it, so you might as well. Here we go. Just plug in back into y equals -2x squared. I didn't clear the last one. -2x squared plus 2x plus 2. Hit graph. I forgot to change my window. If you want to go back to standard, just hit zoom 6. That works for me. Z standard, and nice. Okay. And then we just need to find that maximum point. Second trace maximum. Left bound, enter. Right bound, enter, enter. Looks to be about 0.4999. That's just 0.5, right? And then 2.5. So that's my answer. 0.5, 2.5. 0.5, comma, 2.5. And then here's a good tip. If you use a calculator to solve a problem and you say, show your work, here's how you show your work. You say, I graphed in calc and then found the max. And that's showing your work because you told me what you did. You told me your thinking, right? That's the idea. You show your thinking. Okay. Ready for algebraically? If you don't want to see this, skip. But if you want to do it this way, it's actually really neat. Okay. So we have another formula, which is also on my board right now. If you want to find the axis symmetry in general form, and it's this: -b over 2a. I don't know why I did these colors like that. -b over 2a. And that's how it works. So you take the negative of the middle term, or the one that's multiplying x, and you divide by 2 times the regular one, right? So this is how you find the axis of symmetry. Well, why does that matter? Well, the axis of symmetry is related to our vertex, right? It's at the same spot. So if we can figure out where the axis is, the x value of it, then we can plug it in and find the y value, okay? So -b over 2a is this for our problem. B is 2. So we have -2 over 2 times -2. Okay, which is this. I'm going to rewrite that too. My 2's have been bad today. Sorry. That is this. This is -2 over -4, which is 2 over 4, which is 1/2, which is 0.5. Okay. So guess what? We got there eventually, right? We just used this formula. -b over 2a, we found out it's 0.5. Now, to find the corresponding y value of the vertex, you plug in 0.5 into this equation. So you go f of x equals, instead of f of x, since we're plugging in 0.5, it is f of 0.5. And you get negative 2 times 0.5 squared plus 2 times 0.5 plus 2, right? I just substituted. Every time I saw an x, I wrote 0.5. And then I'm going to use my calculator. So I know I said I used my calculator, but whatever. Negative 2 times 0.5. Make sure you use parentheses, by the way, if you ever square a number like that. Plus 2 times 0.5. And then plus 2. Am I right? Let's see. Yeah, I get 2.5. So I know my point is at these two, 0.5, comma 2.5. And we got the same answer both ways. Okay. This one's just a little more tricky, obviously, doing it algebraically. Helpful if you don't have a graphing calculator and just any calculator. Okay, so there you go. Moving on. I think we're going to need this. So I'm going to go ahead and preemptively copy it here, because we're going to need all this information again for one of these next problems. So let me do this. I'll hit them with a quick little group, and then I hit them with a quick little copy. Okay, bang. Next page. Yeah, for number 10, we need it for sure. So I'm going to hit it with a quick little, I forgot how to paste on this thing. I'll use my mouse. Hello, Control V. There we go. And then shrink it down just a little bit so it fits over here. Okay, but we don't need that yet because we're doing 9. All right, we're on the last page, by the way. Flying through it. It's only been, I don't even know how long, but here we go. So, number 9, we are trying to find another point on the parabola that has an axis of symmetry at 4, at x equals 4, and one point on the parabola is 1, 2. Now it says sketching a graph might help. And a little life hack, and if someone gives you a little hint like this, it might be a good thing to do. Okay, so sketching a graph might help. Let's sketch a graph. No shame in that, right? There's no pride in doing it without a sketch. I was actually looking back at one of the tests I took in high school or is in college, maybe, I don't know, just today, and I did a problem that I couldn't solve, but all I had in the area to answer the problem was sketches of what I thought the formula looked like on a graph. It got me no points, but it helped, I guess. That wasn't a great example. You should sketch a graph still. Anyway, so here's what I know. Have a parabola. I get to decide what it looks like. But the only thing it needs to have is a line of symmetry at 4, x equals 4, and a point at 1, 2. So the cool thing about sketching is you can decide wherever it is. So I'll say this is 4, and this is my axis. And then all I know is that there's some point at 1, 2. It's like right here. Okay. Now my parabola could go a whole bunch of ways. It could go like this. It could go like this, right? Let's say, just for sake of example, my parabola is something like this. Okay. I know that it's symmetrical because I have a line of symmetry, which means what I'm looking for is this point right here, right? I know because there's a point at 1, 2, on the other side of the graph, there's also going to be a point I can find, and that's what I'm looking for. Okay. But to do that, I have to think about distances between the middle, or my axis of symmetry, and this point. Okay. I know that they're going to be at the same height, right? So at least I know that my coordinate point is going to be something, 2, because my y value is already at 2. But my x value, I have to think about when I was at 1 over here, right? This is my x value of 1. What's that distance from the middle? Well, 1 to 4 is a distance of 3, which means that this point over here from the middle also has to be a distance of 3, which means I have to be at 4 plus 3, 7. So that's my point, 7, 2. And that's your answer. You find the second point on the graph, the one that's a mirror reflection of this other one, and it happens to be at 7, 2. There you go. That's how we answered number 9. All right. 10. Here we go. So this is what we need our little hint for, and this will be on my board, okay? So you just need to basically parse these equations and figure out some key information from it. So number one, we have an equation in general form, which looks like this. And keep in mind, this leading coefficient A tells us which way the parabola opens. So to answer these problems, you would say up or down, right? It's an option select. You select one of the two, up or down. In this case, if I look at the leading coefficient, that's the thing multiplying x squared. It is a positive number, which means I know this opens up like a cup and has a minimum. So this opens up. I just realized that like up looks the same, like this U shape and this U shape. It's a good way to remember it. I could have drawn that. I could have done like this, little mnemonic device. Anyway, versus, oh, wait, I'm gonna go crazy on the next one. Just wait. Anyway, the y value, or the y-intercept, is where you lift our parabola up, right? And that's this +9 right here, tells us the y value. But since the intercept is always a coordinate point, I know that it's at 0, 9, right? Because this is just the y value of my y-int, or my vertical shift. Right? So my y-intercept's at 0, 9. That's a thick 9. I'm going to rewrite that. Boom. All right. And then we just use that from general form. Next one is in factored form. And guess what? Whew. So I said the last one opened up because it was positive. Well, this one's negative, which means it must open, oh, wait for this, D-O-W-N down. Okay, that looks way better in my head. I'm not gonna lie. This is not really looking. It looks like dough, and then an upside down parabola. It opens down. I'm sorry. I thought, yeah, N doesn't really look. It's got that little tail. So anyway, maybe next time I'll think of something better for down. Down like a frown. Anyway, the x-intercepts are right here, right? Now, keep in mind, in our form of the equation, these values are already being subtracted, right? To find the x-intercept, you have to find what value of x makes the function equal to 0, which means it's whatever goes into the parenthesis that cancels it out, right? Or makes the parentheses equal to 0. That gives you a 0 or an x-intercept. And so, because it's x minus 6, the x-intercept would just be 6, right? So it's going to be at the point 6, 0, and same exact logic. What value of x would make this whole equation 0? If I plugged in 10 right here, then this would be 10 minus 10. This whole thing would be multiplied by 0, which means it's just equal to 0, right? So my other x-intercept is at 10, 0. There we go, right? So just use, it's basically, you can think of either the opposite, right? Think of it like this, or you can remember that you're trying to find the value of x that turns the equation into 0. That's how I remember it, at least. Okay. And the last but not least, vertex form. If we know the vertex form, we know the vertex. This one, same thing. It's a negative a, right? This a value is negative, so it opens down. And then the vertex, it's at this, comma this, h, comma k. But same logic as the last time. Keep in mind, h was subtracted up here, which means that I need to take the opposite of whatever this number is, right? That's what the vertex is. In other ways, you can think of it about this as a horizontal shift. We'll talk about it in this problem. This would be to the left 4, right? Because I'm adding 4 inside the function. So my vertex should be at -4, comma 5 because of this. I wrote k in my head, but I meant 5. Because this value right here is k, right? This is where I find the y. And then this is where I find the h, which is opposite of what it says in the equation, right? Because I'm subtracting it up here. So boom, there's your vertex. And you do whatever the vertical shift says. You just say, if it's +5, then it's +5 down here. Okay, number 11. We're so close. We're so close. Describe how the graph of g of x compares to the graph of f of x equals x squared. Okay, what that means is, tell me the transformations from this one to this one, right? How did I transform? That's what they're asking. So I just need to look at the differences and see what they do in my equation, okay? So here's the first thing I noticed that's different between this and this. There's a plus 2. That does not happen here, just x squared. So this plus 2 is weird. And then this minus 6 is also weird. That's not right here, right? Sorry, don't call Munoz. I didn't use those colors. It's okay. Switch it. Blue and purple. Okay, whew, we were close. No yellow and green in this house. So we need to figure out what these two different things do. Well, if you remember, inside of a function, so in this case, inside of parentheses being squared, you would shift to the left 2. Shift to the left 2. Because I'm adding inside the function, I do the opposite. Think about it like a 0, almost 2. Like what value of x would have to be? Minus 2 would be 2 less, right? So shifting to the left 2. That comes from the inside. And then the outside, this minus 6, tells me move down 6. The best way to say this is, instead of shift, I should have corrected myself and say translate to the left 2, and then translate down 6. Sorry, right? But there you go. There's your answers. So that's the difference between these two functions. To the left 2 and down 6 from this one. Last problem. I'm not going to lie. This is the hardest problem on the test. Okay. This one is really tricky because it combines a whole bunch of stuff. It is a transformation problem and a dilation problem. It's wicked. Okay. It's wicked. But we just need to first write this equation, which helps us. Okay. And then if you can write the equation, just note you have a calculator. But I didn't say that. All right. So our parent function, in all of these scenarios, our parent function will be x squared, right? F of x equals x squared. And what we're going to do from there is apply these transformations to this. Okay, so we kind of have to know what this looks like and how to dilate it, right? So here's what I'm going to do. I'm going to take this parent function. I'm going to shift it. I'm going to translate it 6 units up because it tells me to. And then I'm going to translate it 5 to the right because it tells me to. And then I'm going to think about the dilation after I do that. Okay? That makes sense. So let's find a vertex. So I know my original vertex is at 0, 0. That's right here on this graph. Notice I gave you this space because you only need this area because we're shifting. So if I move 6 units up and 5 to the right, that means my new vertex is going to be up to 6 and then 5 to the right here. Okay. So here's my new vertex. I'm then going to graph that function. Okay. I'm going to graph x, and then in parentheses, I know I'm moving to the right, so that's minus 5 squared plus 6. Right? That's this equation, but with these two translations. I kind of reverse logic from the previous problem, right? So this one is because of the 6. This one's because of the right, or sorry, the up and then the right. So keep in mind, I'm not dilating yet. I'm just going to graph the parent function. This is the way I think about it. And here's how I think about graphing x squared, even if I translate it. It's all about distance, right? I know that this point's the middle. This is my axis of symmetry. So I just need to figure out some points to the left of it and to the right of it. What you do to graph the parent function of x squared is think about moving to the right or moving to the left, just like 1, right? So I'm at 5. I'm going to go to 6. To figure out how far up to go, you take the distance you move to the right and square it. So I move to the right 1. 1 squared is 1. And so my output is 1 more than I was before. In this case, if I move to the left 1, negative 1 squared is also 1. Okay. Then, If I move 2 to the right, so if I go from 5 to 7, now I move 2 to the right, I square 2, and I get 4. So I should go up 1, 2, 3, 4. And then same thing symmetrical on this side. And then if I move 3 to the right, 1, 2, 3, square that, I get 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And it's the same thing on the other side. The reason I'm squaring it is because it's to find your output, it's your input squared, right? It's y equals x squared, f of x equals x squared. So in our case, we're just thinking about the input as the distance away from the middle. So I'm going to say this is my distance from axis of symmetry. And to find the parent function, you just square that. Okay, so now we've completed that. It looks like this. Something like this. Okay. Now here's what we're going to do. We're going to finally take our last step and dilate by a factor of 3, which means we're going to graph this. If we dilate by a factor of 3, that changes our leading coefficient. So here's our last step, is to graph 3 times x minus 5 squared plus 6. Okay, and I'll do that in green. Here's how you do it. All you have to think about now, instead of left to right, think up and down. When I was over here, I went up 1, right? I went over 1, up 1. Now, because I'm stretching it by a factor of 3, I'm going to go the same distance over, but now I'm going to go 3 times what I went up. So instead of going up 1, I'm going to go up 1, 2, 3. Here and here. My vertex stays the same, right? My vertex stays the same, just the distances away from each point changes. Okay, same thing over here. This time, I went from 2 over 4 up, but now I'm going to go 2 over and then 4 times 3 up. That's 12, right? So 2 over is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 right here. And then same thing on the other side like this. And that's a great amount of points because I can see my parabola looks like this. And that's how I do it. You can do it a different way. You can just stretch it if you can do that, if you can think about that. But I like always graphing that parent function and then stretching it. Okay, that's what I like to do. So if you're getting dilated right bigger, you should have a thinner graph. The bigger your number, the thinner the graph. The closer you are to 0, the wider the graph, right? It's like a fraction or a decimal. You would actually get wider. Right? But yeah, that's it. That concludes this whole review. Thanks for sticking with me. If it was just for a single problem or the entire thing, look at what we accomplished. It's so pretty. I hope I explained it well enough. I think I went pretty in depth. If you have if you have still a question on how I got something, I would advise going back to the video and see if I explain it. I did this all in one take. I'm pretty proud of myself on that regard. So I might have missed something. I might have messed up somewhere. The chances are pretty high. So if you spot it, leave a comment, and I will address the class with it. But otherwise, I'll see you soon. Thank you so much for watching. If you need to come back for corrections, this is a great resource as well. And then let me know if this works as a good review topic and I can do this more often. I'm going to be for individual lessons on a day. But yeah, thank you and see you around.